Chaos theory.
Chaos theory is a field of study in mathematics, with applications in several disciplines including meteorology, physics, engineering, economics, biology, and philosophy. Chaos theory studies the behavior of dynamical systems that are highly sensitive to initial conditions, an effect which is popularly referred to as the butterfly effect. Small differences in initial conditions yield widely diverging outcomes for such dynamical systems, rendering long-term prediction impossible in general. This happens even though these systems are deterministic, meaning that their future behavior is fully determined by their initial conditions, with no random elements involved. In other words, the deterministic nature of these systems does not make them predictable. This behavior is known as deterministic chaos, or simply chaos. This was summarized by Edward Lorenz as follows. Chaotic behavior can be observed in many natural systems, such as weather. Explanation of such behavior may be sought through analysis of a chaotic mathematical model, or through analytical techniques such as recurrence plots and Poincare maps.
Chaotic dynamics.
In common usage, chaos means a state of disorder. However, in chaos theory, the term is defined more precisely. Although there is no universally accepted mathematical definition of chaos, a commonly used definition says that, for a dynamical system to be classified as chaotic, it must have the following properties. It must be sensitive to initial conditions, it must be topologically mixing, and its periodic orbits must be dense. The requirement for sensitive dependence on initial conditions implies that there is a set of initial conditions of positive measure which do not converge to a cycle of any length.
Sensitivity to initial conditions.
Sensitivity to initial conditions means that each point in such a system is arbitrarily closely approximated by other points with significantly different future trajectories. Thus, an arbitrarily small perturbation of the current trajectory may lead to significantly different future behavior. However, it has been shown that the last two properties in the list above actually imply sensitivity to initial conditions, and if attention is restricted to intervals, the second property implies the other two. An alternative, and in general weaker, definition of chaos uses only the first two properties in the above list. It is interesting that the most practically significant condition, that of sensitivity to initial conditions, is actually redundant in the definition, being implied by two, or four intervals, 1, purely topological conditions, which are therefore of greater interest to mathematicians. Sensitivity to initial conditions is popularly known as the butterfly effect, so called because of the title of a paper given by Edward Lorenz in 1972 to the American Association for the Advancement of Science in Washington, D.C. entitled Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The flapping wing represents a small change in the initial condition of the system, which causes a chain of events leading to large-scale phenomena. Had the butterfly not flapped its wings, the trajectory of the system might have been vastly different. A consequence of sensitivity to initial conditions is that if we start with only a finite amount of information about the system, as is usually the case in practice, then beyond a certain time the system will no longer be predictable. This is most familiar in the case of weather, which is generally predictable only about a week ahead. The Lyapunov exponent characterizes the extent of the sensitivity to initial conditions. Quantitatively, two trajectories in phase space with initial separation diverge. Where L is the Lyapunov exponent. The rate of separation can be different for different orientations of the initial separation vector. Thus, there is a whole spectrum of Lyapunov exponents, the number of them is equal to the number of dimensions of the phase space. It is common to just refer to the largest one, that is to the maximal Lyapunov exponent, MLE, because it determines the overall predictability of the system. A positive MLE is usually taken as an indication that the system is chaotic. There are also measure-theoretic mathematical conditions, discussed in ergodic theory, such as mixing or being a case system, which relate to sensitivity of initial conditions and chaos.
Topological mixing.
Topological mixing, or topological transitivity, means that the system will evolve over time so that any given region or open set of its phase space will eventually overlap with any other given region. This mathematical concept of mixing corresponds to the standard intuition, and the mixing of colored dyes or fluids is an example of a chaotic system. Topological mixing is often omitted from popular accounts of chaos, which equate chaos with sensitivity to initial conditions. However, sensitive dependence on initial conditions alone does not give chaos. For example, consider the simple dynamical system produced by repeatedly doubling an initial value. This system has sensitive dependence on initial conditions everywhere, since any pair of nearby points will eventually become widely separated. However, this example has no topological mixing, and therefore has no chaos. Indeed, it has extremely simple behavior. All points except 0 will tend to positive or negative infinity.
Density of periodic orbits.
Density of periodic orbits means that every point in the space is approached arbitrarily closely by periodic orbits. The one-dimensional logistic map defined by x, 4x, 1, x, is one of the simplest systems with density of periodic orbits. For example, or approximately 0.34549115 minus 0.9045085 minus 0.34549115 is an unstable orbit of period 2, and similar orbits exist for periods 4, 8, 16, etc., indeed, for all the periods specified by Sharkovsky's theorem. Sharkovsky's theorem is the basis of the Lee and York, 1975, proof that any one-dimensional system which exhibits a regular cycle of period 3 will also display regular cycles of every other length as well as completely chaotic orbits.
Strange attractors.
Some dynamical systems, like the one-dimensional logistic map defined by x, 4x, 1, x, are chaotic everywhere, but in many cases chaotic behavior is found only in a subset of phase space. The cases of most interest arise when the chaotic behavior takes place on an attractor, since then a large set of initial conditions will lead to orbits that converge to this chaotic region. An easy way to visualize a chaotic attractor is to start with a point in the basin of attraction of the attractor, and then simply plot its subsequent orbit. Because of the topological transitivity condition, this is likely to produce a picture of the entire final attractor, and indeed both orbits shown in the figure on the right give a picture of the general shape of the Lorenz attractor. This attractor results from a simple three-dimensional model of the Lorenz weather system. The Lorenz attractor is perhaps one of the best-known chaotic system diagrams, probably because it was not only one of the first, but it is also one of the most complex and as such gives rise to a very interesting pattern which looks like the wings of a butterfly. Unlike fixed-point attractors and limit cycles, the attractors which arise from chaotic systems, known as strange attractors, have great detail and complexity. Strange attractors occur in both continuous dynamical systems, such as the Lorenz system, and in some discrete systems, such as the Henin map. Other discrete dynamical systems have a repelling structure called a Julia set which forms at the boundary between basins of attraction of fixed points. Julia sets can be thought of as strange repellers. Both strange attractors and Julia sets typically have a fractal structure, and a fractal dimension can be calculated for them.
Minimum complexity of a chaotic system.
Discrete chaotic systems, such as the logistic map, can exhibit strange attractors whatever the dimensionality. In contrast, for continuous dynamical systems, the Poincare-Bendixson theorem shows that a strange attractor can only arise in 3 or more dimensions. Finite-dimensional linear systems are never chaotic. For a dynamical system to display chaotic behavior it has to be either nonlinear, or infinite-dimensional. The Poincare-Bendixson theorem states that a two-dimensional differential equation has very regular behavior. The Lorenz attractor discussed above is generated by a system of 3 differential equations with a total of 7 terms on the right-hand side, 5 of which are linear terms and 2 of which are quadratic, and therefore nonlinear. Another well-known chaotic attractor is generated by the Rossler equations with 7 terms on the right-hand side, only one of which is quadratic, nonlinear. Sprott found a three-dimensional system with just 5 terms on the right-hand side, and with just one quadratic nonlinearity, which exhibits chaos for certain parameter values. Zhang and Heidel show that, at least for dissipative and conservative quadratic systems, three-dimensional quadratic systems with only 3 or 4 terms on the right-hand side cannot exhibit chaotic behavior. The reason is, simply put, that solutions to such systems are asymptotic to a two-dimensional surface and therefore solutions are well-behaved. While the Poincare-Bendixson theorem means that a continuous dynamical system on the Euclidean plane cannot be chaotic, two-dimensional continuous systems with non-Euclidean geometry can exhibit chaotic behavior. Perhaps surprisingly, chaos may occur also in linear systems, provided they are infinite-dimensional. A theory of linear chaos is being developed in a branch of mathematical analysis known as functional analysis.
History.
An early proponent of chaos theory was Henry Poincare. In the 1880s, while studying the three-body problem, he found that there can be orbits which are non-periodic, and yet not forever increasing nor approaching a fixed point. In 1898, Jacques Hadamard published an influential study of the chaotic motion of a free particle gliding frictionlessly on a surface of constant negative curvature. In the system studied, Hadamard's billiards, Hadamard was able to show that all trajectories are unstable in that all particle trajectories diverge exponentially from one another, with a positive Lyapunov exponent. Much of the earlier theory was developed almost entirely by mathematicians, under the name of ergodic theory. Later studies, also on the topic of nonlinear differential equations, were carried out by G. D. Birkhoff, A. N. Kolmogorov, M. L. Cartwright and J. E. Littlewood, and Stephen Smale. Except for Smale, these studies were all directly inspired by physics, the three-body problem in the case of Birkhoff, turbulence and astronomical problems in the case of Kolmogorov, and radio engineering in the case of Cartwright and Littlewood. Although chaotic planetary motion had not been observed, experimentalists had encountered turbulence in fluid motion and non-periodic oscillation in radio circuits without the benefit of a theory to explain what they were seeing. Despite initial insights in the first half of the 20th century, chaos theory became formalized as such only after mid-century, when it first became evident for some scientists that linear theory, the prevailing system theory at that time, simply could not explain the observed behavior of certain experiments like that of the logistic map. What had been beforehand excluded as measure imprecision and simple noise was considered by chaos theories as a full component of the studied systems. The main catalyst for the development of chaos theory was the electronic computer. Much of the mathematics of chaos theory involves the repeated iteration of simple mathematical formulas, which would be impractical to do by hand. Electronic computers made these repeated calculations practical, while figures and images made it possible to visualize these systems. An early pioneer of the theory was Edward Lorenz, whose interest in chaos came about accidentally through his work on weather prediction in 1961. Lorenz was using a simple digital computer, a Royal McBeal GP30, to run his weather simulation. He wanted to see a sequence of data again, and to save time he started the simulation in the middle of its course. He was able to do this by entering a printout of the data corresponding to conditions in the middle of his simulation which he had calculated last time. To his surprise, the weather that the machine began to predict was completely different from the weather calculated before. Lorenz tracked this down to the computer printout. The computer worked with 6-digit precision, but the printout rounded variables off to a 3-digit number, so a value like 0.506127 was printed as 0.506. This difference is tiny, and the consensus at the time would have been that it should have had practically no effect. However, Lorenz had discovered that small changes in initial conditions produce large changes in the long-term outcome. Lorenz's discovery, which gave its name to Lorentz attractors, showed that even detailed atmospheric modeling cannot in general make long-term weather predictions. Weather is usually predictable only about a week ahead. In 1963, Benoit Mandelbrot found recurring patterns at every scale in data on cotton prices. Beforehand, he had studied information theory and concluded noise was patterned like a Cantor set, On any scale, the proportion of noise-containing periods to error-free periods was a constant, thus errors were inevitable and must be planned for by incorporating redundancy. Mandelbrot described both the Noah effect, in which sudden discontinuous changes can occur, and the Joseph effect, in which persistence of a value can occur for a while, yet suddenly change afterwards. This challenged the idea that changes in price were normally distributed. In 1967, he published How Long is the Coast of Britain? Statistical Self-Similarity and Fractional Dimension, showing that a coastline's length varies with the scale of the measuring instrument, resembles itself at all scales, and is infinite in length for an infinitesimally small measuring device. Arguing that a ball of twine appears to be a point when viewed from far away, zero-dimensional, a ball when viewed from fairly near, three-dimensional, or a curved strand, one-dimensional, he argued that the dimensions of an object are relative to the observer and may be fractional. An object whose irregularity is constant over different scales, self-similarity, is a fractal. For example, the Menger sponge, the Sierpinski casket, and the Koch curve or snowflake, which is infinitely long yet encloses a finite space and has a fractal dimension of circa 1.2619. In 1975, Mandelbrot published The Fractal Geometry of Nature, which became a classic of chaos theory. Biological systems such as the branching of the circulatory and bronchial systems proved to fit a fractal model. Chaos was observed by a number of experimenters before it was recognized. For example, in 1927 by van der Pol and in 1958 by R. L. Ives. However, as a graduate student in Chihiro Hayashi's laboratory at Kyoto University, Yoshisuke Wada was experimenting with analog computers and noticed, on November 27, 1961, what he called randomly transitional phenomena. Yet his advisor did not agree with his conclusions at the time, and did not allow him to report his findings until 1970. In December 1977, the New York Academy of Sciences organized the first symposium on chaos, attended by David Bruell, Robert May, James A. York, coiner of the term chaos as used in mathematics, Robert Shaw, a physicist, part of the Uemans group with J. Doane Farmer and Norman Packard, who tried to find a mathematical method to beat roulette, and then created with them the Dynamical Systems Collective in Santa Cruz, California, and the meteorologist Edward Lorenz. The following year, independently, the French Pierre Collet and Charles Tresser with the article Iterations Endomorphisms at Group D Renormalization, and the American Mitchell Feigenbaum with the article Quantitative Universality for a Class of Nonlinear Transformations described logistic maps. They notably discovered the universality in chaos, permitting an application of chaos theory to many different phenomena. In 1979, Albert J. Liebschuber, during a symposium organized in Aspen by Pierre Hohenberg, presented his experimental observation of the bifurcation cascade that leads to chaos and turbulence in Rayleigh-Benard convection systems. He was awarded the Wolf Prize in Physics in 1986 along with Mitchell J. Feigenbaum for his brilliant experimental demonstration of the transition to turbulence and chaos in dynamical systems. Then in 1986, the New York Academy of Sciences co-organized with the National Institute of Mental Health and the Office of Naval Research the first important conference on chaos in biology and medicine. There, Bernardo Huberman presented a mathematical model of the eye-tracking disorder among schizophrenics. This led to a renewal of physiology in the 1980s through the application of chaos theory, for example in the study of pathological cardiac cycles. In 1987, Purbach, Chao Tang and Kurt Wiesenfeld published a paper in Physical Review Letters describing for the first time self-organized criticality, SOC, considered to be one of the mechanisms by which complexity arises in nature. Alongside largely lab-based approaches such as the Bach-Tang-Wiesenfeld sand pile, many other investigations have focused on large-scale natural or social systems that are known, or suspected, to display scale-invariant behavior. Although these approaches were not always welcomed, at least initially, by specialists in the subjects examined, SOC has nevertheless become established as a strong candidate for explaining a number of natural phenomena, including earthquakes, which, long before SOC was discovered, were known as a source of scale-invariant behaviors such as the Gutenberg-Richter law describing the statistical distribution of earthquake sizes, and the Omori law describing the frequency of aftershocks. Solar flares. Fluctuations in economic systems such as financial markets, references to SOC are common in econophysics. Landscape formation. Forest fires. Landslides. Epidemics. And biological evolution, where SOC has been invoked, for example, as the dynamical mechanism behind the theory of punctuated equilibria put forward by Niles Eldredge and Stephen Jay Gould. Given the implications of a scale-free distribution of event sizes, some researchers have suggested that another phenomenon that should be considered an example of SOC is the occurrence of wars. These applied investigations of SOC have included both attempts at modeling, either developing new models or adapting existing ones to the specifics of a given natural system, and extensive data analysis to determine the existence and/or characteristics of natural scaling laws. This same year 1987, James Gleick published Chaos, Making a New Science, which became a bestseller and introduced the general principles of chaos theory as well as its history to the broad public, though his history underemphasized important Soviet contributions. At first the domain of work of a few, isolated individuals, chaos theory progressively emerged as a transdisciplinary and institutional discipline, mainly under the name of nonlinear systems analysis. Alluding to Thomas Kuhn's concept of a paradigm shift exposed in The Structure of Scientific Revolutions, 1962, many chaologists, as some describe themselves, claim that this new theory was an example of such a shift, a thesis upheld by J. Gleick. The availability of cheaper, more powerful computers broadens the applicability of chaos theory. Currently, chaos theory continues to be a very active area of research, involving many different disciplines: mathematics, topology, physics, social systems, population biology, biology, meteorology, astrophysics, information theory, computational neuroscience, etc.
Distinguishing random from chaotic data.
It can be difficult to tell from data whether a physical or other observed process is random or chaotic, because in practice no time series consists of pure signal. There will always be some form of corrupting noise, even if it is present as round-off or truncation error. Thus any real-time series, even if mostly deterministic, will contain some randomness. All methods for distinguishing deterministic and stochastic processes rely on the fact that a deterministic system always evolves in the same way from a given starting point. Thus, given a time series to test for determinism, one can pick a test state, search the time series for a similar or nearby state, and compare their respective time evolutions. To find the error is the difference between the time evolution of the test state and the time evolution of the nearby state. A deterministic system will have an error that either remains small, stable, regular solution, or increases exponentially with time, chaos. A stochastic system will have a randomly distributed error. Essentially, all measures of determinism taken from time series rely upon finding the closest states to a given test state, for example, correlation dimension, Lyapunov exponents, etc. To define the state of a system, one typically relies on phase space embedding methods. Typically one chooses an embedding dimension and investigates the propagation of the error between two nearby states. If the error looks random, one increases the dimension. If you can increase the dimension to obtain a deterministic-looking error, then you are done. Though it may sound simple, it is not really. One complication is that as the dimension increases, the search for a nearby state requires a lot more computation time and a lot of data. The amount of data required increases exponentially with embedding dimension to find a suitably close candidate. If the embedding dimension, number of measures per state, is chosen too small, less than the true value, deterministic data can appear to be random, but in theory there is no problem choosing the dimension too large. The method will work. When a nonlinear deterministic system is attended by external fluctuations, its trajectories present series and permanent distortions. Furthermore, the noise is amplified due to the inherent nonlinearity and reveals totally new dynamical properties. Statistical tests attempting to separate noise from the deterministic skeleton or inversely isolate the deterministic part risk failure. Things become worse when the deterministic component is a nonlinear feedback system. In presence of interactions between nonlinear deterministic components and noise, the resulting nonlinear series can display dynamics that traditional tests for nonlinearity are sometimes not able to capture. The question of how to distinguish deterministic chaotic systems from stochastic systems has also been discussed in philosophy. It has been shown that they might be observationally equivalent.
Applications.
Chaos theory was born from observing weather patterns, but it has become applicable to a variety of other situations. Some areas benefiting from chaos theory today are geology, mathematics, microbiology, biology, computer science, economics, engineering, finance, algorithmic trading, meteorology, philosophy, physics, politics, population dynamics, psychology, and robotics. A few main categories are listed below with examples, but this is by no means a comprehensive list as new applications are appearing every day.
Computer science.
Chaos theory is not new to computer science, and has been used for many years in cryptography. With more powerful computers available, encryption experts must continue to develop better methods to keep information safe. One type of encryption, secret key or symmetric key, relies on diffusion and confusion, which is modeled well by chaos theory. Another type of computing, DNA computing, which when paired with chaos theory offers a more efficient way to encrypt images and other information. Robotics is another area that has recently benefited from chaos theory. Instead of robots acting in a trial and error type of refinement to interact with their environment, chaos theory has been used to build a predictive model.
Biology.
For over 100 years, biologists have been keeping track of populations of different species with population models. Most models are deterministic systems, but recently scientists have been able to implement chaotic models in certain populations. For example, a study on models of Canadian lynx showed there was chaotic behavior in the population growth. Chaos can also be found in ecological systems, such as hydrology. While a chaotic model for hydrology has its shortcomings, there is still much to be learned from looking at the data through the lens of chaos theory. Another biological application is found in cardiography. Fetal surveillance is a difficult balance of obtaining accurate information while being as non-invasive as possible. Better models of warning signs of fetal hypoxia can be obtained through chaotic modeling.
Other.
In chemistry, predicting gas solubility is essential to manufacturing polymers, but models using particle swarm optimization tend to converge to the wrong points. An improved version of PSO has been created by introducing chaos, which keeps the simulations from getting stuck. In celestial mechanics, especially when observing asteroids, applying chaos theory leads to better predictions about when these objects will come in range of Earth and other planets. Traffic forecasting is another area that greatly benefits from applications of chaos theory. Better prediction of when traffic will appear would allow measures to be taken to disperse it before the traffic starts, rather than after. Combining chaos theory principles with a few other methods has led to a more accurate short-term prediction model. Even economic models can be improved through chaos. Predicting the health of an economic system and what factors influence it most is an extremely complex task. Many of the indicators of financial health are chaotic in nature, so including those characteristics lead to better overall estimations. Geology is yet another field that is improved when given access to chaos theory. Coal mines have always been dangerous places, so knowing when gas leaks would occur could save an immeasurable number of lives. These gas leaks have chaotic tendencies that when properly modeled can be fairly accurately predicted. Chaos theory can even be applied outside the natural sciences. By adapting a model of career counseling to include a chaotic interpretation of the relationship between employees and the job market, better suggestions can be made to people struggling with career decisions.
Cultural references.
Chaos theory has been mentioned in movies and works of literature, including Michael Crichton's novels Jurassic Park and The Lost World, as well as their film adaptations. The films Chaos and The Butterfly Effect. The Indian movie Days of Atharam starring Kamal Hassan. The sitcoms Community and Spaced, Tom Stoppard's play Arcadia, and the video games Tom Clancy's Splinter Cell, Chaos Theory, and Assassin's Creed. In the computer game The Secret World, the Dragon Secret Society uses chaos theory to achieve political dominance. Ray Bradbury's short story Sound of Thunder explores chaos theory. Chaos theory was the subject of the BBC documentaries High Anxieties, The Mathematics of Chaos directed by David Malone, and The Secret Life of Chaos presented by Jim Al-Khalili. Cultural permutations of chaos theory are explored in the book The Unity of Nature by Alan Marshall, Imperial College Press, London, 2002.